Hey everybody, welcome to Math with Ace. We are focusing on statistics today and we are keeping our momentum going for probabilities, and we are working on two-way tables. A two-way table is also called a contingency table, and it allows us to easily calculate conditional probability, intersections, unions. It's a very nice way to organize your data. We're going to do a couple of examples here in this first video. The table that is given to us here is already complete. There are totals and values. All of the rows sum to a certain value, all of the columns sum to that same value. And we're going to go through the table and calculate a few different things. So first of all, we are asked to find the probability. This is a study of speeding violations in drivers who use cell phones, and it's a fictional study. So we're asked to find the probability that a driver is a cell phone user. So in my chart, I need to find where cell phone users are. So these are users of cell phone, and I'm highlighting the entire row because I am concerned with all of the cell phone users, and that is 305 out of the total 755 individuals. I'm just looking at the overall total. The next question asks me to find the probability that a driver had no violation in the last year. So no violation is in columns, and I have these here. There are 685 out of 755. Standard, totals, straightforward. Now I'm asked to do a little bit more complex probabilities. I want to find the probability that a driver had no violation in the last year and was a cell phone user. Well, no violation is here. That's all these individuals. Cell phone users are here. And where they intersect is actually the one that's almost so dark you can't even see it. But that was the 280. It's where these two intersect. There are 280 that were users of cell phones and had no violation out of 755. So and is where the two intersect on your two-way table. It's like Battleship. Your row and your column come together. That is where the intersection occurs. The next question says, find the probability that a driver is a cell phone user or had no violation in the last year. Or, okay, cell phone user or had no violation. Okay. Now, I could talk about all of the cell phone users, which is 305 out of 755. Or this is the general addition rule. No violation, 685 over 755. But that's going to give me 990. How can I have 990 when there's only 755 individuals? These two events are not mutually exclusive. They can occur, and their intersection is not zero. So the general addition rule says I need to subtract away their intersection, what they have in common, of 280 in order to not double count them. That's a probability of 710 out of 755. Because if you notice, when I did the highlight of the pink, I highlighted the 280. When I did the highlight of the yellow, I also did. So I'm double counting it when you're just adding totals. So it's important that you take away the intersection since they're not mutually exclusive. What is the probability that a driver is a cell phone user given the driver had a violation? So here's what's happening. You have the entire group of 755 people, but then they say, I only want to look at the people that had a violation last year. So everybody else, please sit down. So only those that are standing are the group that I'm talking about. Well, how many were in that group? Given a driver had a violation. Where are my violations? Speeding violations right here. Of you 70 that are standing, how many of you are cell phone users? That's 25. That means that my probability becomes 25 out of 70 because I'm only concerned with those that had a violation. Let's use that same approach for the last problem. If the driver had no violation last year, find the probability they had no violation last year given they were not a cell phone user. So who are the group? that remain standing, it's those who were not cell phone users. So my not cell phone users here, there's 450 of us. And essentially, we need to ignore everything else. We don't care about the overall totals. We don't care about the cell phone users. We only care about those that don't use a cell phone. And of those 450 that are still standing, how many had no violations? 405. That's 405 out of that 450. Okay, let's use this same approach and actually fill in a table as well. We have a random sample of 100 hikers. 100 means the total is 100. And the areas of hiking they prefer. Is that true? Is 45 plus 55 100? Yes, it is. Now we have women and not women. We have the preference of coastline, near lakes and streams, or mountain peaks. And the way that our rows add up, they should add up to 45 and 55, and our columns should add up to specific values as well. This is a puzzle. So let's fill in the pieces that we know. We knew 45 and 55 sum to 100. But what is 18 and 16 plus something to 45? So I can use the fact that I have two values, and then the unknown is going to get me to 45. So I can, instead of doing addition, I can use the inverse operation of subtraction and say 45 minus 18 and minus 16, which is 11. So 18 plus 16 plus 11 does get me to 45, and I found that missing piece. Well, now I can figure out how many prefer mountain peaks. 11 plus 14 is 25. I can also use subtraction to find lakes and streams. 16 plus something should give me 41. So if I do 41 minus 16, I find out that there's 25 who preferred lakes and streams. I can do the same thing to find either not women or the total. Let's do 100 minus 41 minus 25 to figure out how many prefer the coastline. That's 34. And then 34 minus 18 would give me this piece here. So you just start with one that you can actually solve and then work backwards using subtraction to fill in the other pieces, or addition if you need it. So we completed the table. Now I'm asked, are being a woman and preferring the coastline independent events? In order to determine independence, you can do that one of three ways, and you only need to do it one of three ways. So if you do it one way and get your answer, great. You don't need to prove all three ways. I can say that the probability of event A and event B is equal to the probability of event A times the probability of event B. That's one way. Or I can use conditional probabilities to determine, is the probability of A the same as A given some condition? Is the probability of B the same as the probability of B given some condition? Any of those would work. I'd say let's go ahead and calculate the first one, the probability of A and B. So what is the probability of being a woman and preferring the coastline? Is that equal to the probability of being a woman times the probability of preferring the coastline? Woman and coastline, woman is here, coastline is here, and where they intersected was 18. So that's 18 out of 100, which is 18% or 0.18. Is that equal to the probability of being a woman, which was 45 out of 100, right here, or 45% or 0.45, times preferring the coastline? There were 34 that preferred the coastline out of 100, or 0.34, 34%. So I need to multiply, and it's easier for me to multiply the decimals equivalents, which gives me 0.153 or 153 thousandths. Is that equal to 18 hundredths? No, it is not. And because they are not equal, they are not independent. If you want to check it another way, that's totally fine. You cannot use either of the two conditional probabilities. All right, let's approach our next question. Find the probability that a person is not a woman given the person prefers hiking near lakes and streams. So what is the probability that you are not a woman given you prefer lakes and streams? And they tell us the notation, use N for not a woman and L for lakes and streams. So given lakes and streams, so just like the before where we had people sit down, I want everybody that doesn't prefer lakes and streams to sit down because all we care about are those that prefer lakes and streams. So U41 are the ones I'm looking at. Of U41, how many are not a woman? 25. Now, the rule for conditional probability says the probability of n given L is equal to the probability of n and L divided by the probability of L. So that's saying the intersection of not a woman and lakes and streams, 25 out of 100, divided by the probability of lakes and streams, should be equal to the same thing we calculated. When we've been doing conditional probabilities with complex fractions, what you do is you multiply by the reciprocal. That's the rules for dividing of fractions. And I can reduce the 100 and 100 because it's like 100 over 100, which is 1. And 25 times 1 times 1 times 41 gives me 25 over 41. It's the same thing. But notice how easy it was to look at the chart and find where they focused and look at that total. Let's do the last problem. Find the probability that a person is a woman or prefers hiking on mountain peaks. So I want the probability that is a woman or prefers mountain peaks. This is the general addition rule, and if they have anything in common, if they're not mutually exclusive, then we don't want to double count. So let's look at the chart. Woman or prefers hiking on mountain peaks. So where the double shading occurred was at 11. So I would want to say woman, which is 45. Let me write the notation for you without the numbers really quickly. This is the same thing as the probability of being a woman plus the probability of preferring mountain peaks minus the probability of being a woman and preferring mountain peaks, so I don't double count you. The probability of being a woman was 45 out of 100. The probability of preferring mountain peaks was 25 out of 100. And the probability of being a woman who prefers mountain peaks and mountain peaks is 11 out of 100, because that 11 was included in the 45 and it was also included in the 25. So 45 plus 25 minus 11 gives me 59 out of 100. So the probability of being a woman or preferring mountain peaks was 59 out of 100. Thanks for watching. I hope you continue this series of videos on probabilities with two-way tables, and then we'll get into Venn diagrams and tree diagrams.